So where does performance fit within this kind of relationship? Well, this is from Ekblom, published again early 2000s, but Ekblom writes this really important statement. The hemoglobin concentration at rest and during exercise, and that's the oxygen content in the arterial blood, in well-trained athletes is no different from that in untrained individuals of the same sex and age. So that's quite fascinating, that you would think hemoglobin concentration at rest and during exercise is different. Actually, there isn't a massive difference between the two groups. But there is a huge difference between the sexes. Now, this is relatively old data from Ekblom's group going back to 1972. And what you've got here is 3 case studies. And what they've done is they have recorded, we've got our oxygen uptake here, VO2 max. And then what you've got here is maximal work time. And this block here is kind of the measures pre. And then what they've done is they've donated blood here, so they've had blood removed, so it's blood loss, and then what they've done is they have reinfused the blood. Now this is quite an important point. So what they've done here is they've taken the blood out, and not surprisingly, what you'd expect to see, we haven't got the graph here, but what you'd expect to see is that the blood volume decreases, hemoglobin concentration decreases, as you saw in that earlier graph earlier on. It would be this kind of similar response. You'd see the hemoglobin concentration fall. But you notice it is by day 5 it's starting to bounce back, day 6 and 7 and starting to bounce back to this normal concentration. So you would in essence get that hemoglobin concentration back. But what they've done in this study is they've allowed for it to bounce back, and it's taken around about 28 days for it to bounce back. But then what they've done is they've taken the blood volume that they took out, which they've frozen, and they've now reinfused that back in. So they fundamentally now expanded blood volume, they've expanded enormously red blood cell count, hemoglobin concentration, and so on. And then what they have done is they have recorded the VO2 max values. And you can see, not surprisingly, when you donated blood, it fell. But as the blood volume is re-expanding, they start to increase. But you put this additional volume of blood back in, you reinfuse it into the circulation, there's a significant increase in both work time and the VO2 max, because you've fundamentally increased the oxygen carrying capacity of the blood. It's a very, very unique example of showing how fundamentally important the hematology of the individual is into the oxygen carrying capacity. Not surprisingly then, there is a very bold relationship, particularly between hemoglobin and performance. And that association is what you see here, which is what's called the oxyhemoglobin dissociation curve. So here you've got the partial pressure of oxygen on our x-axis, and then on the y-axis you've got the percentage of hemoglobin. And so when we have got a high partial pressure, what we have is we have a high retention in terms of oxygen bound to hemoglobin. But as the pressure starts to fall, the amount of oxygen bound to hemoglobin starts to decline. And this is the fundamental connection between pressure and O2 release. The release of oxygen is fundamentally pressure dependent. So the pressure in the lung, the PO2 in the lung, is higher than the PO2 in the circulation. The PO2 in the circulation is higher than the PO2 at the cell. The PO2 at the cell is higher than the PO2 in the mitochondria. So fundamentally, as the pressure starts to decline, the amount of oxygen that is bound to hemoglobin starts to decrease, because we fundamentally are going to release that oxygen as the pressure declines. And this is a fundamental trick, biological trick, that is used to allow us to release oxygen across different structures within the body. So the affinity that hemoglobin has for oxygen is absolutely dependent upon its partial pressure. So if you're under a high partial pressure, more oxygen is bound to hemoglobin. If you've got a low partial pressure, I fundamentally, if you think about it very logically, it means that I need to get more oxygen into the cell. It's no good retaining the oxygen on the cell. It needs to be released from the cell into the on the blood cell. It needs to be released from the blood cell into the cell where it is needed for example, to facilitate things like metabolism. And not surprisingly, there is then a mechanism which connects O2 release and CO2 production. The key thing to understand is that what drives, in essence, metabolism to a certain degree is not O2 availability, it's CO2 production. So the other thing to recognise is that the release of oxygen is linked to the amount of CO2 being produced in the cell. So not only have you got an association between the partial pressure of oxygen and the amount of oxygen being released, but you've also got the association then between the increase in the CO2 in the cell, which is a function of an increase in metabolism, and the amount of oxygen being released. Because the CO2 concentration goes up, as the PCO2 goes up, the amount of oxygen being released starts to go down. We fundamentally get this leftward shift in the oxyhemoglobin dissociation curve. So the net result is it affects the amount of oxygen being taken up in the mitochondria. And you can kind of see this association a little bit more. Here you've got VO2 max, and what they've done is they've correlated here against hemoglobin mass. And what you can see is a very, very neat association. It doesn't matter really which grouping you're looking at in here. You know, whether you're looking at, for example, males or females, which are represented by our two different groupings. It doesn't really matter. You can see there's this positive association between the two. The higher the hemoglobin mass, overall mass, the higher the VO2 max. Now it is correlation rather than causal, but it is contributory to the VO2 max. We absolutely know if you've got somebody who's anemic, look at the effect. I've got a low hemoglobin concentration, I have a very, very low VO2 max. If I've got a high hemoglobin concentration, so I come up here, I'll have a much higher VO2 max. Now there are clearly other factors that affect the VO2 max, but this really kind of sets the scene up for us in terms of understanding that kind of key relationship. Now this data here is quite unique. This is data that was taken fairly recently, 2013 paper. And they've got 6 days of racing, highly trained cyclists. And what you can see here is the changes in plasma volume. Again, it doesn't matter which line you're looking at. Over the course of a 6-day cycle race, you can see that plasma volume changes, quite a significant change, because the riders are retaining fluid, because one of the issues that you have when you're competing is it's difficult to get fluid in, consume fluid. So one of the simple things that happens is we retain fluid. We have this ability to store more fluid in the plasma to compensate. At the same time though, there's an interesting reduction in the hemoglobin concentration. And one of the main reasons for that is that you're putting the body under an awful lot of stress when you're competing. And although we need to facilitate an increase in red blood cell production through the process of stress and fatigue, unless we've got an adequate recovery between successive days of training, that hemoglobin will not bounce back. And in fact, this looks very similar to what we saw earlier on with that blood donation data set where the hemoglobin concentration is falling. As we come out of the racing period, you can see the hemoglobin concentration is starting to bounce back. And then finally, it is just worth thinking about the fact that blood volume actually changes during exercise. And this is quite a unique insight. What we know is during an actual exercise intervention, there's around about a 20% reduction in plasma volume. And that's primarily to compensate for the increase in core temperature. And so one of the ways in which we can keep the temperature maintained is actually release fluid from the plasma volume as a way of keeping the body cool, and also you release some of that in the form of sweat. If we then look at data from Ron Morn, they postulated, and his group postulated, about a 10 to 15% reduction in plasma volume within the first few minutes of exercise. Quite significant. And you know, that is fundamentally to do with shifts in fluid within the body, but it's quite a large reduction early on. But Noakes was suggesting, which is fascinating, that actually if you take somebody who's doing prolonged running, you get a deformation of the red blood cell in the foot. Because of the ground impact forces between the foot and the surface, you get around about 2 to 3% reduction in red blood cell count because of foot strike. Fundamentally, the foot hits the ground, you compress the red blood cell, they break. And so you lose some of the red blood cell count. Now, whether that is reduced to a certain degree using the kind of the more focused running shoes that we have now, which they've got the carbon strips in, things like the Vaporflies, I don't know. but it would certainly be more evident, for example, if you're working with the military, where they're using the very sturdy boots and they're marching over long distances.